So, after going through optical microscope, let us see some more problem with any optical system. Okay. So, already we have seen the one of the issues with any microscope which is related to resolution, that how close I can bring two objects and still I will be able to see them as two different entities. Other than that, there are more problem with optical system, and these are called optical aberrations. Okay. You must be wondering, for example, you can get a camera for like 3,000 rupees, 5,000 rupees, and the price of a camera can go up to 1 lakh rupees, okay, in a SLR camera. And you must be wondering that why some cameras are coming so cheap, they are getting you the same photograph. Okay. In case of optical microscope also, you will see that some optical microscopes are coming as cheap as 25,000 or 30,000 rupees, and some optical microscopes are costing us around 3 or 4 lakh rupees. Okay. So, there is a large variation in the prices of cameras or microscope and so on. And one of the reason for this wide variation in the pricing is because how you produce these optical systems, okay, basically lenses, and whether they are aberration free or not. Okay. So, just making a lens or an optical system aberration free add to the cost, okay, and I tell you it is very expensive to make a perfect optical system, okay, so that you can get rid of all the aberrations in the optical system which are introduced because of the lenses which we use. Okay. So, when you buy or your friend buy a expensive camera, okay, do not make fun of him, because he has spent money in getting that kind of optical system. So, in our ideal optical system, okay, basically what we want is that all rays which are coming from the object, they should fall on the same point to get a very clear and sharp image. Okay. But this is not what happens. Okay. You have variation in the focal point depending upon different type of aberrations. Okay. So, basically because of this aberration, the light focuses at different point, okay, and we will see that what are these different aberrations. Okay. Some are because of the lens, okay, some are because of the light or electromagnetic radiation which we use. Okay. So, we categorize or classify this aberration based on that. Okay. So, one of the most important aberration is called spherical aberration, okay, and as you can see on the slide, it says the rays furthest from the optical axis focus near the lens, then the rays closer to the optic axis. Okay. So, let me show you this particular aberration by a schematic here. Okay. Again I am making a lens here, okay, and suppose I have a light source, okay, let us say I am getting all parallel rays here on the lens. Okay. So, in this ray diagram, the rays which are closer to the edge of the lens, these are called marginal rays. Okay, all these rays are called marginal rays, and the rays which are closer to optic are called paraxial rays. Okay. Now, the spherical aberration says that the rays which are marginal rays, they have focus at a focal point which is closer to the lens, okay, and these paraxial rays, let me draw it with some other pen, okay, they kind of focus at a position further away from the lens. Okay. So, there are two focal points depending upon from which part of the lens the rays are converging. Okay. A photograph sent by one of my friend, and his name is also given there. He gave me this photograph, and you can see that in the center the image looks focused, okay, but the features which are on the periphery of that, okay, they are all look slightly out of focus. Of course, there is some kind of change in the angle also of that particular feature, but the main thing to see here is that when you look at the outer portion, okay, they look out of focus, and that you can see in your normal magnifying lens also, which we use at home, okay, and you try to read it, any newspaper or anything, or you try to see any object using this, okay, and what you will notice that you are reading only from the center of the lens, okay, because that is where you are focusing or your focus is best, okay, and the remaining portion, okay, is kind of slightly out of focus, okay, the rays which are coming from the periphery of the lens. So, what happens now? Suppose I keep my screen or my eye at this point, okay, what will happen? The features which are on the outer side of the lens, that will be in focus, and the features which are coming from the center of the lens, they will be out of focus. If I change the position of a screen to this one, okay, what will happen now? The center portion features are clear to me, but outer portions are usually out of focus, okay, and that is what you can see in this particular image in the slide also, that the center portion looks more or less focused, but the outer portion is looking out of focus, okay. So, that is what is the spherical aberration, okay. So, usually good lenses or good microscope are in that this particular problem is taken care, okay. So, you will not see a spherical aberration. The next one comes because of the light or the electromagnetic radiation which we use, okay, and this is called chromatic aberration, okay. So, what is chromatic aberration? It occurs when a range of wavelength is present in the light. So, our visible light, our white light or white radiation has multiple wavelengths, okay. It is composed of a range of wavelengths, okay, from red up to blue, green, blue and so on, okay. And when this kind of light goes through a single lens, okay, it causes light to be deviated by an amount depending on its wavelength, okay. So, blue will be the closest to the lens and red will be further away from the lens, okay. So, again let me draw a schematic here. So, this is my lens, okay, and suppose a white light is falling on the objective here, objective lens here, okay, or any lens here, okay. Now, depending upon the wavelength, so this particular ray which is composed of different wavelengths, okay, now it will get converged depending upon its wavelength. So, as we said, the blue will be the closest, okay, then comes the green wavelength, okay, and then you will have red one. Okay. Slightly draw it better. Okay. So, now what happens in this case if my screen or my eye, if it is here, okay, at the blue one. So, a blue image will be clear and there will be a halo of red and green around the image, okay. If my eye or screen is here, then the reddish that image will be clear, and there will be a blue halo around the image. Okay. So, there will be after the features or whatever is the edge of a building or something, okay, you will get some multiple colors next to that particular image. For example, here a pigeon is shown, I have taken it from this website, okay, and you can see that there is a red halo around the where the edge of this the body of the pigeon is there, okay, there is a red halo around that. Okay. So, because we are not focusing at that particular image, okay, that particular halo is being shown here. Okay. So, this kind of multiple image, okay, so one light is diffracted into different rays, okay, and you will get this multiple image of different colors, okay, superimposed on each other. Okay, and that will of course bring down the clarity of the images. You can see in these two images, this one is very clear, okay, does not have that problem, and this one has the problem, and you cannot see features. For example, if you want to see the sharpness of the beak of this particular pigeon is not clear, where it is in this case it is very clear. Okay. So, this is what is the chromatic aberration, usually because of the multiple or range of wavelength if you use in a visible light. Okay. The next comes is astigmatism. Okay. In this, what happens that depending upon the plane through which the rays are passing, okay, your image, the focal point will change depending upon that. Okay. So, let us take for example this lens. Okay. So, if my image is going through this vertical plane, okay, that will have a different focal point than the image which is going through this horizontal plane. So, it will have a different focal point. Okay. Of course, it is little bit difficult to draw this thing. So, I have taken this particular image from again another website. Okay. So, this red one light which is going through the vertical plane, okay, it has a focus at some point here, and the yellow light which is going through the horizontal plane of the lens has a different focal point. Okay. This type of problem also come in a human eye. Okay. So, a lot of time the people who wear glasses, or maybe some of your friend who wear glasses, okay, if they do not have this astigmatism problem, their lens will be on the prescription. If you go to the doctor, it will be written as spherical, okay, spherical lens of this much power. If you have astigmatism, okay, then in your prescription it will also be written as cylindrical. Okay, there will be a cylindrical lens in conjunction with the spherical lens, okay, to correct the astigmatism which has come in your eye. For example, in my case also, I have in my right eye I have astigmatism. So, my lens has some power of spherical lens and some power of this cylindrical lens, okay, to correct the astigmatism in my eye. So, basically again the problem is the rays which are coming from in this vertical plane has a different focal point, and which is coming from the horizontal plane has a different focal point. So, to correct that, okay, to make the image at the same at the retina, okay, both should come at the same point, okay, I have to have a cylindrical lens is also there coupled with the spherical one. Okay. You will not be able to see the difference in your glasses, but it will be there. Okay. So, this is the problem which we call as astigmatism. Two different image will be forming depending upon the from which plane the rays are going. Okay. Now, of course, when you have these problems, there must be corrections also, and as I told you then that when you do all these corrections, that add to the cost of the microscope or a camera, for example. Okay. So, there are few lenses which are available in the market. Okay. So, when you want to buy a microscope, or if you go in the market to buy a microscope, you have to specify that I want this particular objective or this particular eyepiece. Okay. So, one of the cheapest one in this is what we call as achromatic objectives. As you can see, it is a combination of convex lens and a concave lens, half concave, and they are made of two different materials, okay, to change the refractive index. And by doing all this jugglery of combination and two different refractive index, they are able to correct the chromatic aberration here, and they are able to bring all the wavelengths together at one single point. Okay. So, in achromatic objectives, they are corrected chromatically for red and blue light, okay, they bring it to common focus. It is also corrected for spherical aberration for the color green. Okay. So, green light, for green light they have also corrected it for spherical aberrations. Okay. Now, you will understand if you have gone into your metallography lab, okay, a lot of time we use these green filters. Okay. So, what this green filter does, that one thing it does is that it has eliminated all other wavelengths from your light. Okay. So, you have only one radiation now, which is green. So, you do not have to worry about chromatic aberration because you are using only one wavelength. The other thing is that some of these lenses, as for example achromatic objectives, are corrected for green light for spherical aberration. Okay. So, using a green filter get you a much better result because chromatic aberration will not be there, spherical aberration will not be there, okay, because the lens is corrected for that. Okay, and that is why in black and white imaging it works better in this case with green filter, because most of your aberrations are taken care of. Okay. Then there are more complicated lenses in the market, okay, and these are called semi apochromates. Okay. These objectives are corrected chromatically for red and blue light, and also they are closer to the green focus. The fluorides are corrected spherically for two colors, blue and green. Okay. So, now they spherically also they have corrected in this particular lens for both blue and green. Okay. The next which is the one of the most expensive objective is apochromatic objectives. These objectives are corrected chromatically for 4 colors, deep blue, blue, green and red, and they are spherically corrected for 2 or 3 colors, deep blue, blue and green. Okay. And on the slide you can also see that these different lenses are shown here. Okay. So, first one is achromate, 10x achromate, second one is 10x fluoride or semi apochromates, and the third one here is again 10x apochromate. Okay. And just look at the complexity of the lenses here. Okay. When we see a microscope, we see this objective or this eyepiece, we think there must be one lens which we usually draw as a schematic, and we think, oh, there will be one lens and it is doing all the job. Okay. But it is not so. You see it that there are so many double lenses are there, one will be convex, one will be concave or half concave, there is another doublet here. So, this whole big lens piece contains so many different small lenses in combination. Okay. Also, this material for each of these lenses will also be different, it will not be same, okay, as we just saw in the previous example. Okay. Now, if you go from achromate to fluoride, in achromate only 2 doublets were there. Now, there are 4 doublets. Okay. Some meniscus lens is there, then some doublet here, another doublet here, one more. So, now you see that complexity of objective has increased, and now you have to add these many objectives in the system. Okay. And these many lenses in the system with different combinations. Okay. And for each of these lens, okay, the making is a very tedious process. You have to have a very nice curvature on that. Okay. For example, astigmatism also, if you see, it is a manufacturing defect. Okay. So, while making the lens, okay, you could not maintain the same radius of curvature at each point. Okay. Somewhere the radius of curvature has changed. Okay. And that is why in vertical plane and horizontal plane, okay, you have different focal point. So, astigmatism is a manufacturing defect, okay, which you can eliminate if you have a better manufacturing capabilities. Okay. So, when you add these many lenses, okay, you can see that for each lens you have to have good manufacturing capability to get lens without any defect in the lens. Okay. Then of course, apochromate you see more complexities, okay, more lenses are there. Okay. So, you can understand that the cost of the microscope increases almost exponentially with change in the type of objective we are using. Okay. So, when you go to any manufacturer and if he is saying that he is going to supply you apochromate, okay, he is going to charge you for that. Okay. And of course, the quality of image which you will get will be exponentially better than what you will get from a simple achromate. Okay. So, these are some websites which from which we took some of the images here. Okay. So, just to acknowledge that we took, and some you will also, if you go through this website, you will also understand the lot of details about microscope and of course camera and other optical systems. Okay. And with that I would like to say thank you today. Okay. I think this particular lecture will be of interest to you because you understand that how microscopes are made and what are the different components of a microscope. Thank you.